passageways and the bundle itself. Assembling and disassembling the casing requires a piece-by-piece assembling and disassembling of the rotor as well. Now that we've seen the outside of the compressor, let's take a closer look at the internal components. Inside the casing is the rotor. Rotors usually consist of a solid center shaft with impellers keyed and pressed onto the center shaft. In most centrifugal compressors, rotors are built with a balanced piston installed at the discharge end to relieve the thrust-bearing load. Stacked rotors consist of a stub shaft for each end, several impellers, a balancing piston, spool pieces, and other needed parts, all held together with a heavy center bolt. Although this type of rotor is always used in a stacked style vertically split casing, it can also be used in other types of casings as well. The impeller is the most critical part of a centrifugal compressor because its size, shape, and speed determine the compressor performance. Most often you'll find two types of impellers, closed and semi-open. In a closed impeller, shrouds cover both sides of the blades. On one side, a central hole or eye allows gas to enter the impeller. But closed impellers are the most common and are mainly used in multi-stage compressors. In the semi-open impeller, a shroud completely covers and forms a solid backing for one side of the blades. Semi-open impellers are used for large gas flows and are generally used only on single-stage compressors. The blades, or vanes, on an impeller can be straight, curved forward, or curved backward. Backward curved vanes are the most efficient and stable. However, since backward curved vanes cause the gas to leave the impeller with less velocity, there is less velocity to convert to pressure. Most oil-filled centrifugal compressors use the backward curved vane impeller. The balancing piston is fixed to and rotates with the shaft. It is surrounded by a seal that minimizes leakage from the upstream side of the shaft to the downstream side. The downstream side of the balancing piston is piped back to the compressor's suction side through a balancing piston leak-off line. This causes a pressure difference across the piston that provides a net thrust on the shaft to compensate for the thrust being exerted on the impellers. Near the inlet and between stages of the compressor are guide vanes. They're used to direct the flow of gas into the eye of the impeller at just the right angle. This is important because efficient performance and stable operation of the compressor depends on the velocity and direction of the gas entering the impeller eye. Guide vanes can either be fixed or adjustable. Adjustable guide vanes are usually available on single-stage compressors and are sometimes used in the first stage of multi-stage compressors. These vanes can either be adjusted manually or automatically to control the angle of the gas flowing into the eye of the impeller to keep it running stable and efficient over a wider operating range. As the gas leaves the impeller, it's forced into a passageway in the casing called the diffuser. The diffuser forms an increasingly larger path for the gas to flow through. Now let's look at how each stage in a multi-stage centrifugal compressor is separated from the next. All the parts that make up one stage of a multi-stage centrifugal compressor can be found on a single-stage compressor. One stage is separated from the next by a specially designed part of the casing called the diaphragm. The adjacent walls of individual diaphragms form a diffuser passage. After the gas travels through the diffuser, it passes through the return channel of the diaphragm. Diaphragms can be horizontally split or fully circular. In large horizontally split compressors, the heat from gas compression can cause the case to expand, which in turn expands the diaphragms. If this happens, lower gas pressure and leaks could result. Sometimes this problem is corrected by circulating cooling water through the channel. In stacked casing designs, the diaphragms are one piece and therefore provide greater stability and strength. In addition, the one-piece design eliminates interstage leaks and helps contribute to higher efficiency. Most compressors need some type of sealing to keep the compressed gas from leaking out of the compressor and to prevent leaking between stages. Particular care must be taken when the gas is combustible. That's one reason why seals are so important. Let's examine some of the types used. The most common types of seals are the labyrinth, liquid film, carbon ring, and mechanical. The simplest type of seal is a labyrinth seal. It has a series of grooves machined to sharp knife-edge thickness that maintain a close clearance to the mating part. It can either be stationary or rotating. The mating parts are made of a softer material such as babbitt, so they will wear before the labyrinth does. Labyrinth seals can be found in multiple, stepped, and interlocking configurations. Sometimes carbon rings are included with the labyrinth seal. On high pressure and heavy-duty compressors, liquid film seals are the most common. A typical seal consists of 2 or more rings that don't rotate, but are free to float with shaft movement. Oil is injected between the rings at a pressure higher than the compressor suction pressure. This allows the oil to flow between the seal rings and the shaft and then into the oil drains. Labyrinth seals guard against any oil leakage into the gas stream. Emission regulations sometimes require the use of liquid film seals. These seals provide a barrier fluid which prevents leakage of processed gas to the atmosphere. Carbon rings, on the other hand, are dry contact seals, which consist of several high-quality carbon rings held in place by stainless steel spacers and axial springs. The entire seal assembly can be removed from the compressor when worn or broken segments need replacing. In some applications, a buffer gas is used in conjunction with the carbon rings to separate the gas in the compressor from the surrounding atmosphere. Also, you'll find combinations of carbon rings and labyrinth seals are also used. Another type of seal is the mechanical contact seal. It consists of machine rotating and stationary surfaces that remain in direct contact with one another to prevent leakage. Mechanical contact seals are primarily used for low-pressure gas that has no corrosion components. One typical form of the seal uses a rotating contact ring, a full floating carbon wear ring, a stationary mating ring, and a spring-loading device. A small quantity of lubricating oil is used to remove frictional heat. This type of seal provides some sealing whenever the compressor is shut down. Not only do we have to seal against leaks, but we have to guard against any unwanted movements of the shaft as well. And that's where bearings play an important part. Inside the centrifugal compressor are forces that tend to cause the shaft to move in a forward and backward direction, commonly referred to as axial motion, and a side-to-side direction, commonly referred to as radial motion. For example, an unbalanced impeller can cause radial motion. Self-aligning tilting pad bearings are used to support the shaft and prevent radial and axial motion. In most large centrifugal compressors, a tilting pad journal bearing is used. This type of bearing is designed to prevent the rotor oscillations associated with the standard sleeve-type journal bearing. As the shaft rotates, a wedge-shaped film of oil produces a stabilizing force that tends to reduce vibration. This self-aligning property will compensate for any misalignment and will tend to distribute the loads evenly. To control the axial motion of the shaft, thrust bearings are used. They are usually of the double-acting tilt pad design, so that thrust loading in either direction can be supported. A typical thrust bearing has a thrust collar attached to the shaft and thrust shoes arranged in a circular bearing case. Between the thrust collar and thrust shoes, an oil film is used to support the thrust load. Almost any large machine needs some type of lubrication, and the centrifugal compressor is no exception. Without the proper lubrication, frictional heat could build up to a dangerous level, possibly damaging the compressor. That's why lubrication systems are so important. Most centrifugal compressors use external lube oil circulation systems to lubricate and cool all bearings and gears in the compressor and accessory drivers. A typical lubrication system consists of an oil reservoir, an oil pump, a filter, and a cooler. Inside the reservoir, special baffles are built in to prevent the oil from foaming. Now here's how the lube oil system works. Oil is pumped from the reservoir through a filter to a cooler, where it is cooled to the correct operating temperature. This cooled, clean oil then flows under pressure to each bearing through holes and grooves. Gravity allows the oil to make its way back into the oil reservoir, where the cycle starts all over again. Most lube oil systems also have an auxiliary pump and dual filters. These help give added protection to the lube oil system. Now let's look at another circulating oil system, the seal oil system. Oil film seals are used on many compressors to positively seal the production gas inside the casing. In some situations, a separate seal oil system is used. However, in most cases, a combination lube oil and seal oil system is used. Sometimes a buffer gas system might be used along with the lube oil and seal oil system, if necessary. Seal oil enters the space between the seal rings from an overhead seal oil tank. Oil which has been used only for lubrication drains back to the reservoir. Seal oil, which may have come in contact with gas, drains into drain pots for removal of the gas. The separated oil is then returned to the reservoir for recirculation. One thing you should always remember about lube and seal oil systems: always make sure that any oil removed from the sumps or reservoirs is disposed of using approved methods. All right, you've seen how the lube oil system helps lubricate the working parts of the compressor and in turn reduces heat from friction. Now let's look at how we reduce the heat in the gas we compress. Heat is generated when gas is compressed. That's why for safe and efficient operation of the facility, the compressed gas must be cooled. Also, high gas temperatures make it difficult to lubricate the bearings and other moving parts. This is particularly true if the gas is to be recycled through the compressor, because hot suction gas will overheat the compressor and cause serious damage. In many large compressors, the gas flow is changed from the typical straight-through arrangement. The gas is actually taken out of the compressor at an intermediate pressure and circulated through a heat exchanger called an intercooler. Here, the gas is cooled before it is returned to the compressor at another point. On very large multi-stage compressors, there may be several intercoolers. Even with intercooling, discharge gas may still be too hot for delivery. In these cases, the discharge gas is passed through a heat exchanger or aftercooler before it's delivered to the pipeline. In this section, we've shown you in detail all the parts that make up the compressor and what they do. And we've taken a brief look at its auxiliary systems. In our next section, we'll be getting familiar with drivers, couplings, and controls. But first, stop the videotape and take some time to review your student manual and answer the questions at the end of this section. I'll see you when you're finished. You know, the work in airplanes' propeller